Good afternoon, everyone, and welcome to our webinar today on uncertainty propagation for force calibration systems. I'd like to welcome back Henry Zumbrun, our force calibration expert from Morehouse Instrument Company. Today, we're very grateful to have him to give us a presentation on topics related to force. Henry, next slide. So before we get started, just a few things. As you may already have noticed, everyone right now is muted and will be muted for the entire session of this webinar. But please feel free to utilize the question toolbar. It should be on your far right of your screen. And what we're going to do is review your questions and answer them at the end. All of these webinars are being recorded. And they will be available later on PJLA's website that you can download if you have to skip out for any reason. Okay, so with that, Henry, thank you. I want to turn this over to you, and we look forward to your presentation.
Yeah, thank you, Tracy. Thank you, PJLA, for having me. Yeah, hopefully people are here, they want to learn something new about doing some uncertainties for force calibration. And we're going to go over the basics today. As Tracy said, questions and answers at the end. If you have questions during it, just type them in the box as you have them. Presentation should be somewhere in the 45 minutes time frame, and then we can do some questions and answers. As Tracy said, my name's Henry Zumbrun, president of Morehouse Instrument Company. Been in metrology for over 25 years now. My preferred contact method, even though I have H. Zumbrun and MH Force here, is LinkedIn. So if you're on LinkedIn and you are not connected to me, please connect to me via LinkedIn. I do like having that and to answer questions on LinkedIn. And good questions often inspire blogs and articles and all this other stuff if we haven't answered them before. A little bit about Morehouse is, we're a manufacturing company located in York, Pennsylvania, East Coast, where today it's about 80 some degrees, and we calibrate force and torque. Primarily, we do much more force than torque, but we happen to buy the second most accurate torque standard in the world from an NMI, which was a very, very interesting. So these opportunities do not come up often where an NMI actually sells equipment and gets out of doing one parameter per se. And we ended up buying the machine for NPL, which means we had NPL scientists with us for about 5 weeks. And during the day, we just would learn and learn and learn about torque. And then during the night, we would drink with the NPL scientists, and they became good friends and everything else. So very grateful for that experience. And maybe future we'll do some torque stuff. Our purpose, why we do these things is, and why people show up to work at our facility and become part of our team is we hope that, through things like this, that we can create a safer world by helping companies improve their force and torque measurements. It's all it's really about. If you're missing a big component of uncertainty or you're missing some things on loading conditions or something else, and we can help you make better measurements, that's fantastic. That means you're passing more instruments. Likely your PFA, probability of false accept, is going down, and you're actually saying things that are good. And when you say things are bad, they actually are bad. So that's really the goal of a lot of this, right? Is a reliability and conformity on top of it. So when you start with uncertainty and that propagation of uncertainty, make sure you have that correct. It's one of the first steps. So really important discussion today. Things we'll talk about are force systems and uncertainties, comparison of existing guidance documents that are out there. There's some in ASTM E74. I like this standard. It's just, I know not everybody's going to follow the standard. It's a legal metrology standard. It's something that gives you a good sense of how good that equipment is when it's used in similar conditions. That's all. I can talk a little more about it. Explanation of tiered system for force calibration standards. Some practical examples of uncertainty calculations at different tiers, and then a little bit of error sources. There's a lot there. Hopefully, if you want to learn more about error sources, you can go to our website, and I can pull that up and show you. The webinar aims to give attendees comprehensive understanding of uncertainty, probably and force calibration, enable improved accuracy and reliability. So other things, I'm going to discuss why Morehouse developed a method to calculate force CMCs, a general overview of typical force systems and their uncertainties, and recommendations for calculating calibration and measurement capability, which sometimes I'll say CMC. That is what I'm talking about, calibration and measurement capability. So the why go to this effort? We have several guidance documents on there to go write a guidance document, be part of it, do that, share it with the community. Really, because we have NCSLI RP12, which kind of lumps everything together. And there's the section right now. We're fortunate that we have AI. If you don't have the lock wizard versions of things and stuff like that, you can dump these things into AI and you can say, hey, talk to Chat GPT, Claude, or whatever you might use, and you can extract some good stuff from really good stuff from all these documents here, and it's worthwhile to read them as well. But NCSLI RP12 is very daunting, and the section, they just like throw everything into a budget, and I'll show that. Euromet CG4, some people may say, yeah, that's Europe. They use a bit different method, and it relies on having the transducer calibrated to ISO 376. And I know we have some people on this webinar, hopefully some know what ISO 376 is. It's basically the European standard, not equivalent to E74, but kind of is. You need to calibrate to ISO 376 to perform calibrations to ISO 7500. ASTM E74 is similar in that you do calibrations to E74 here to calibrate to ASTM E4. Though the standards are different, so they're not really equivalent. It's just about the same, and there's a lot more to the ISO 376 standard. So a lot of people in North America, and when I say numbers like a lot, that's pretty vague. I'm talking like 90-some% of our business is calibration to E74, other calibrations, maybe 10% is ISO 376. So from our point of view, ISO 376 is used in North America, though by just a smaller percentage of people. So if you haven't heard about it, don't worry about it. It's probably not relevant to what you're doing unless you're in Europe or some of the other parts of the world. And then ASTM E74 has an appendix. It is a good start. There's some good recommendations in it, though it's not taking in degrees of freedom and all this other stuff. It's basically just RSSing, and it doesn't have all that you need. And then there's just lack of, like looking at this, there's lack of designated guideline for calculating force uncertainties when using a standard such as E74 or others that, accreditation bodies like PJLA and the other ones would use for calculating their calibration measurement and capability to verify you're calculating it, depending what side you're on. So Euromet CG4, in my opinion, it was the most complete document. It's 23 pages total. NCSLI RP18, there's pages 75 to 93. It's 18 pages, but only 5 specifically deal with a load cell. Then amplifiers are added as part of DC voltage. Not that many people use amplifiers. I would guess the number of people we have, maybe a couple out of the whole group of people attending. And then the ASTM appendix is 7 pages, and it basically ends with, hey, take U times all of this stuff squared, and RSS square root of the sum squared, all that fun stuff. And CSL RP12, if you go there, it's gonna say something like this: calibration of rated load cell sensitivity, all this stuff. But if you have your system calibrated in accordance with one of the standards, such as 376 or ASTM E74, some of this stuff's just not needed. You'd be very wrong to put in nonlinearity and hysteresis if you're having your load cell calibrated to ascending and descending and assigning coefficients. So anyway, there's a lot here. I joke that it sounds like they took a load cell spec sheet and just threw whatever was on it and said, move on. The other thing that we see happening when I talked about E74 is someone might use components of uncertainty, and they just say, okay, let's throw them all in, right? And we'll add the reference lab CMC, we'll do all this, and we'll just root some, square them, and we'll say, okay, here, my expanded uncertainty to significant figures is this. But that's only for one part of the range, right? It's only for one single point. If I say my, at capacity, it's 1.21, what about like repeatability down at the low end? What if, resolution, it's there, it could get quite dominant and everything else. So if those that know this stuff pretty well, the recommendation is to use the Wells-Satherthwaite equation, but I'll get more into that. This load cell, particularly that I did this workup was calibrated in accordance with the E74 standard, yet no mention of this critical component to uncertainty, which is called the lower limit factor, which is a type A, and statistically, it's probably the lion's share of all of these numbers here if we put that back into this budget. So we see that happening all the time. Somebody goes and gets their equipment calibrated, and then they use the spec sheet and only the spec sheet for their uncertainty and do not understand how they all come together. So, and then they put a percentage. The other thing is this, what I was getting at, and kind of bumbled a little bit, but it was at the percentage. You say, okay, 1.21 pounds is on the scope. Okay, fine. And then they say, okay, well, that's 0.6. Well, I'll round this up to 0.65 and I'll put that on my scope. However, that number right there is constant, and at 10%, 0.061 becomes 0.61. So we see a lot of that stuff going on too, is that you're not taking the full range and just converting into a percentage, but that percentage is only of that actual value, and this one at 2,000 pounds. Just things to think about. So what we did, made some things. I took the E74 appendix, took most of the requirements of it with JCGM, that's the GUM Guide to Uncertainty and Measurement in 2008. And we produced two guides. The more generic guide at the bottom was done for more than just a calibrated in accordance with ASTM E74. It was done if you have just a 10-point calibration. If you have this, we put guidance in for that. We put guidance in for ISO 376 as well. The one at the top is, hey, if you have one of our machines or somebody else's machine, doesn't really matter, you can still follow it. And this is how I want to do my budget. So I recommend the one at the top for most people if you really want a really good analysis of uncertainty. And that one at the top starts with things like this. I'm going to break my uncertainty down into typically type A and type B uncertainties. And my type A, that one on top, should have a lower limit factor reduced to 1 standard deviation, and the ASTM is reported with a K value of 2.4. So when I reduce that, you get a certificate, it says, hey, your load cell was calibrated by X, your lower limit factor is this. You reduce that out to divide that by 2.4. A repeatability of the best existing device and repeatability and reproducibility between operators. Those are all type, potentially, most of them are type A. Type B, resolution of the best existing device, reference standard resolution, reference standard uncertainty, reference standard stability. Stability can be type A or B, and environmental factors and other error sources. Stability would be type A if I had like 10 years worth of data and I did statistical analysis on it. We could likely move it up and getting to some more advanced stuff here. Though the reason this slide is here is because my cal was done in accordance with E74, and if you look at it, there's not much on the spec sheet besides probably environmental factors. I would take side load sensitivity and some other things, but what people end up doing is they throw in this SEV nonlinearity or hysteresis instead. So the way the E74 standard works is you assign coefficients, polynomial equation with coefficients that tell you that, hey, when I apply this force, my instrument should read this, and it does that curve fit for you, and therefore negates the need for nonlinearity of that system. So I made, or whatever, I think it's we now because I had help. Those several weekends of my life, I spent making this Excel sheet. It is available on our website. And the Excel sheet, just as a guidance doc, walks you through everything. So you get the full range of forces. We have repeatability numbers here, and here I only filled out 3 of them, but you can do 4. You can add to it. It's unlocked, so use at your own discretion. But you can take the formulas, you can do all kinds of different stuff. And it just explains how to do all of this, and temperature, report repeatability data to engineering units. Sometimes if you're working in millivolts per volt, you're working in divisions, you're working in something else, you can convert it all to engineering units. Lots of math in here, lots of different screens, and it will use the Wells-Satterthwaite equation and do a full range. So what we typically get, so that's some of how to do it, but what we typically get, because people ask, is like, how good can my system be? E74 on a typical uncertainty tiers for force calibration, you get primary standards, which are dead weights, calibrated to to the SI, adjusted for air buoyancy, material density, and local gravity. So force has that been determined there, that what you're going to correct for. And then tier 2 are devices you start at. Probably the best you start at is 001, and then you're going to transfer that uncertainty. So tier 2 is going to get a bit larger. Tier 2 is secondary standards or instruments such as load cells, proving rings, or other force measuring devices which have been calibrated by the primary standards. So now tier 3, we're likely using secondary standards to calibrate on something else. Maybe we're calibrating force gauges, maybe more load cells, maybe crane scales, dynamometers. And that can fall typically all over the place, but typically 0.05 to 0.5%. So this is much larger per se than the first tier, right? And then it keeps getting larger and larger. And then devices for force verification are going to be greater than 0.5% to 5%. And that's usually a testing machine. Further dissemination of forces in common after this tier then certainly becomes quite large. So this is really contained for E74. And you can see they build it in such a way that you have ratios built into all of this. And that the end goal is to likely calibrate a 0.5% or 1% testing machine following these steps. Now, force is used everywhere, so the end goal could be calibrate a sensor that goes in your car to detect if somebody's in the seat to deploy the airbag or not. Much less accurate than what I'm showing, or much higher uncertainties than what I'm showing there, typically for that. You just don't need to be that good. You just need to know if somebody's sitting in the seat or not. So when we're actually using equipment to make different measurements, primary standards right here, just showing different, this is our equipment. If we start at 0.016, weights calibrated directly by NIST, and then we calibrate a load cell, that load cell is then used in another machine. That other machine, probably the best we're going to get is around 0.02%, and it depends on how many transfer changes that we make. One load cell by itself is not going to have the range that most people think it will, meaning if I want to maintain 0.02% of applied force, I'm likely going to need a lot more than just one load cell throughout a range to do that. And then tier 3, calibration and working standards. There we have like a bench top with load cell, different equipment, and CMCs typically vary 0.03 to 0.5% there on a testing machine. Talking about the weights and what you would do, that tier 0, you have weights calibrated hopefully by reference, a really good reference laboratory. In our case, it's NIST. Though there's several mass labs out there, even our state can adjust and correct for local gravity, air buoyancy, and material density. You have to give them that information, and you have to give them that target weight. So there's some calculation that you may need to do. On our website, there is a guidance document and an Excel sheet that will do mass to force, where you can enter all this stuff in and do the calculations for you on what your target should be. Though in that case, you need to know you still do need to know the material density, air buoyancy, and local gravity. And there's the formula for that. And then here's a view down from our machine here. Weights picture were right. They were adjusted at NIST, and traceability is still derived, even though we changed. At least at this, it's still derived from the International Prototype Kilogram SI symbol. So, you know, some people more analytical and ask how we determine gravity at our location. So a simple answer is I took a bathroom scale and I drove to NIST, and they let me come to the location with their weights, and I weighed myself on the scale, brought it back, and then weighed myself again after a 2-hour trip. Now, of course, I'm kidding. There's a whole joke on somebody using a bathroom scale to set the weights. They were not an accredited organization, but they would do everybody's scales in the region at a price that was very favorable. So people used them because they were cheap, and it turned out the guy was using his bathroom scale as a comparator to do the other sets. So that's where that came from, just a stupid story that actually happened. No, NIST derives their traceability, and that's how we get it. We adjust our weights. We have local gravity done on site. We have coupons of the material at different levels for our machines, where somebody like, Tron or Rice Lake or some will do a density analysis of those to give us the actual material density. And then we monitor our air buoyancy, and we have a device for that. It's like 0.001. I forget it off the top of my head, but yeah, we have a Vasella device that we've been monitoring for take a year's worth of data and buoyancy and calculate it out that way. So if we're going to do uncertainty analysis, it starts with, okay, so we use NIST. Great. Cool. You use NIST. We have to include their reference uncertainty in anything we do, right? And then we're going to have to figure errors due to the material density, gravity, air density, environmental temperature. And we did have our gravity calculated in the 1990s, and then we had it calculated again in 2022, and it changed by about 0.1 part per million in the facility. So really low change. Was happy that matched out. Probably won't get it done again with that very, very low number. The other thing we're going to do, typically there's this talk in some of the guidance documents about best existing device. So we're going to use a best existing device to conduct repeatability studies. How do we know how good our equipment is, right? Unless, we can do the propagation, though, unless we put equipment in there, start to run process control charts and start to do other things and start taking a lot of measurements. It's just numbers on paper at some point, right? So you haven't actually put something in a machine. It could bend, it could do all types of things. You could introduce side load, all types of error sources are present. What I like to say for force, if the best machines are plumb level, square, rigid, low torsion, and you are never perfectly level, you always have torsion, you always have some bending in the system, so you can take it from that. There's the same slide I showed before, and basically on this one, we're just saying, okay, these are what we're doing here. We're going to take that tier 0, and we're going to calibrate a load cell. And we're going to hopefully calibrate it in accordance with E74, which gives us a really good reproducibility condition of the instrument, which is going to become one of our major components for uncertainty. And we calibrate that cell in a deadweight machine using ASTM E74. The latest standard is 18. It does need revised, and that's going to give us a lower limit factor. That lower limit factor standard uses a method of least squares to fit the polynomial function to the data points. And then you take this multiple runs of data, 3 runs of data, you rotate the instrument, and you're rotating it because your machine's not perfect. And any imperfections are likely going to show up in that. The instrument itself is not perfect. No one makes anything that's super, that's perfect. If you keep going out decimal places, you'll always find some variation in things. So anyway, we're going to take that, the deviations divided by the number of samples minus the degree of polynomial fit. That's the formula at the bottom that ASTM uses. A coverage factor of K, which should be italicized, shame on me. And then we're going to do all this, reduce that, and hopefully we'll get some type of number. Like the lower limit factor is 0.0214 units. Now, I use our Excel sheet and do repeatability studies, do everything else. We're going to put that in there, and this is just one blown up version of that Welch-Satherthwaite equation at 200 pounds of force. And what's interesting here, and why are you showing 200 pounds of force, is because this number, if you look right here, the expanded uncertainty with everything included is 0.021%. So let's look at our contribution here. This is why I like this tool a lot better than RSSing, and there's a number of reasons I like that. So if you say, hey, I want to get better, what can I do? Oh, maybe this repeatability. Maybe I need a better existing device, right? Maybe I need a better control. I mean, that is the largest contribution to our uncertainty right there. So this automatically gives us something, if we want to get better than 021, that we probably want to improve the repeatability. Maybe, like I said, maybe that's automation. Maybe that's the technician. Maybe they need more time to make measurements, to fine tune and to hold the forces and all of that other stuff that come into play. So that repeatability data that I showed you that was the largest needs to be taken for various test points throughout the loading range. This example only shows 1 point and 4 points. Maybe that number is larger, and if we want to get that down, maybe we need to take more measurements. Maybe we need to take 5, 6, 7. A general good rule for any load cell I'm going to use as a reference standard would be to take a repeatability point every 10% for the loading range. And we've seen a lot of loading ranges where the bottom end of it is nowhere near as good as the top end of it. And that makes sense. Sometimes the resolution is a deciding factor. I have papers on that. And there's the VIM definition of repeatability condition of the measurement. And you just say that it includes the same measurement procedure, same operator, same measuring system, same operating conditions, and same location, and replicate measurements of the same or similar objects. And when we talk about reproducibility, now we're saying, hey, this could be different locations. It's not with any of the examples I give you in this budget. Different operators, different measuring systems, replicate measurements on the same or similar objects. And then MSA 4th edition had this, which I kind of liked. It says the traditional between appraisers variability, reproducibility is typically defined as a variation in the average of the measurement of a different during measuring the instrument with identical characteristics on the same part. You can get into all types of statistical analysis here. You can do ANOVAs. Greg Senker, who I know has done some stuff with PJLA, he has a lot of good stuff out there on some of, and he has a new paper coming out in Quality that talks to this quite a bit. So what we're generally going to do here, remember, we've taken that load cell, we've done repeatability, we've done it throughout our range. If it's a 2,000 pound load cell or 2,000 Newton or whatever units you want to work in, we want to do a point at least every 10% of that range. And now here we're saying, okay, let's find out, let's do different technicians. I only put 2 in this example here. So let's take different technicians and see what's going on with them. Typically, if I have 5 technicians, I'm going to use all 5 technicians and do some type of R&R. If I have 6 technicians, I'm going to use 6. If it's only me, I'm probably just going to do technician 1 and I'm going to do me again in general. I know some labs have that. And then I'm going to figure out what that reproducibility condition is. If it's really high, it could be something, maybe my force equipment. Maybe it's the device I'm using. Maybe it's the force equipment is not, it really doesn't have, maybe I have some side load. Maybe it's not really plumb level, square, and rigid as it needs to be. The other contributions there, resolution, look, that's what you're reading. The smallest change in the quantity being measured. And then we have ILAC P14 definition. Some people just thrown in there. Best existing device is understood as a device to be calibrated that is commercially or otherwise available for customers, even if it has special performance stability or has a long history of calibration. You know, if you're doing this for force calibration, I see people all the time use like junky load cells or devices that aren't as good, and then they do not get good numbers off of their equipment. And it's like, so what I say, very stable load cell and indicator with enough resolution to observe differences. That's the other thing. If we had a 2,000 pound load cell and we set the resolution to 20 pounds, I would imagine it's going to be perfect. And that's not going to be that many counts now, is it? It's only 100 counts. So we're going to have a problem if we do that. So we want to have enough resolution as well. For the test I did, the resolution was 0.01 force units. And then reference standard calibration uncertainty, usually measurement uncertainty of the reference standard used. If we're using dead weights, great. Our dead weight machine, as I said, calibrated directly by NIST. We have a realized uncertainty of about 0.0016%. And what our sheet does, if you enter engineering units, you can leave this blank, and then we have forms that if you are using a static number, like, hey, I 1 pound at 2,000 and maybe 0.2 pounds at, anyway, it's there and can be used. That's why I put it in there. Reference standard stability. I typically use, hey, load cells over time can be very, very stable, and this is where you make a decision, right? I typically use the previous calibration and compare it, and that's rectangular. The change in output from one calibration to another, you just compare multiple cals over time. Like I said, I typically, the way this sheet is made, it's one to the other. You can, I have worked it out where you can put multiple years of calibration data in, standard deviation of mean. You can do all kinds of things. I typically, as I said, I typically find that the best representation here is comparing against the previous calibration. Then we get into things, the other things like we add temperature, right? I have specifications on my load cell. This is where I actually go to my load cell specification sheet. I'm going to go here and say sensitivity effect on temperature is such 0.08. Well, I convert that. Let's work in Celsius because ASTM and some other standards say, hey, you have to maintain your calibration plus or minus 1 degree C. In which case, I convert Fahrenheit to Celsius. It amounts to about 0.0015% per 1 degree C. If you're operating in 3 degrees C, you'd be at 0.0045%. It's pretty easy to do. The other things you could add in here, zero effect unrated, you could look at this. You could also look at side load sensitivity. We look at this a lot. You can look at creep. Creeps generally, some of this stuff in here that people do throw in, a lot of times, depending on how you're taking your return zero and whatnot, it's often counted as part of your R&R and your repeatability. You're going to detect some of this stuff inherent in the system, and especially if you run control charts, which I cannot recommend enough. That over time you're just you're gonna balance some of these out, and that's why I'm not calling on them specifically in the examples. Other things that you could have other error sources. There's a whole list here. I said here, creep recovery and return, side load sensitivity, but not switching standards. If you want, Morehouse has, I have a 333-page book on everything force. related. It's taken me a long time to write it. As I said, it's 333 pages. It talks about all of this stuff and more. So if you really want to dive deeper, this webinar does not have enough time to cover the whole 333 pages. So if you really want to dive deeper, you can download that. I'm just starting to skim the surface with some things here. Misalignment, just some things to be aware of. You know, say Morehouse calibrated your stuff. We got really good results because we centered everything, and then maybe a technician goes out in the field and doesn't pay attention to centering or uses a different machine, and all of a sudden the numbers do not look like they should. This is just a really bad load cell, and that's why I put it here, because the lines are there. The load cell looks pretty aligned in both pictures, but if you examine them, this one over here is a little off. So you can just slightly see it if you look at the line in reference to the connector. There's probably only like 1/8 of an inch difference, and it's just the output just went crazy. I've seen this. It's not very, very common. This is one of those extreme examples. So it is something to pay attention to, that everything should be using that primary load axis. And if you're slightly off, or your technician's slightly off, you may get different results. This one's a little more repeatable, different hardness of top adapters on load cells. It's not all load cells are designed and built the same way. These are multi-column cells. Actually, the one to the right is a single column cell. The one to the left is a multi-column cell. And that's just what it means. It means there's one element in the one to the right, and in the one to the left, there's 4 elements with a lot of strain gauges. These cells inherently, depending on what you use on the top of them, produce a different output. So if it comes to our lab and an adapter doesn't come in, we usually ask you about that adapter. If you don't know about that and know that the hardness of adapter changes the deflection of these load cells, there could be a very large error source that's there. And you probably don't capture that until you do an ILC or a proficiency test. And that's where we close the gap on all of this. So I highly recommend, even though this is a CMC, calibration and measurement capability and uncertainty propagation for force measurements, highly recommend, no matter what you're doing, any measurements you're making, is that you participate in good PTs. And use instruments or ILCs. We do a lot of ILCs, and use instruments that are good, that can prove out your uncertainty, so you don't have any of these errors. And read the 333-page book, and it'll discuss everything that you should do and more. This one just had different thread depths. Nothing wrong with this type of load cell. It's a good load cell. Customer just didn't send in their adapters and said, tell me what you did. If we engaged the cell 1.5 inches, we got the cell read 10,000 and 1.5 pounds. And if we engaged it 1/2 inch, it read 9942.3 lbf. So huge difference there. There was a difference of 59.2 pounds on a 10,000 pound load cell. So expected performance was better than 0.25 is what the customer expected. If they change out adapters, they get 20 times that, 0.5, about 0.5%. Another example, this is one I use all the time, tension links, because people do them. Hey, 2 pin sizes, customer doesn't send in what they're using it with. There's a manufacturer's specification. If the lab doesn't use the recommended I think it's an E diameter, it might be F diameter, of whatever the pin is, there could be extreme errors. Here's a difference of 860 pounds or 1.72% error on a device that's supposed to be 0.1%. You can test this. If you run a cal lab or you have equipment, you can rotate your pins around in it in the tension link, or you can test it maybe by using safer pins or loading it to half capacity and just varying that pin size. You most likely would see quite a large difference depending on the design of the tension link. So what we're looking at here, we've crossed all of these off, really. Right, type A contributions, type B, we started, we're talking about right here, we were talking about some other error sources that potentially exist. And then we go to this. Here we go. If we did this for 200 pounds of force, our next step would be, let's do the same thing again for the next point in the range, do 400. 400, look, this is looking a lot better than the 200, right? Almost cut in half, not quite linear. Just depends on our contributions. So 0.21 versus 0.012. If I wanted to maintain better than 0.01, which we do on a lot of our secondary standards, I might have to only use this 2,000 pound load cell from 800 pounds of force to 2,000. You know, that's the benefit of doing these multiple points and doing everything else, as you can see. And here, just looking at that, repeatability between technicians, a little different way to show things. Repeatability between technicians, largest error source. And that was, there's not using dead weights. So basically on this one, we're doing a cal of a load cell in dead weights and looking at the results, and we're getting 0.02. How about our reference standard? We only change our reference standard, and instead of using 0.00116, and we use a reference standard that's 0.025. What happens? Well, the 02 becomes 031, and that 012 becomes 0.02. The 400 pound force point, the expanded uncertainty more than doubles. At capacity, it becomes like, typically it'll become 5 to 10 times higher. So pretty significant. That reference standard can impact things. This chart or the other equation that I have that shows the contributions, you can just pick it off right there. What if I wanted to lower my uncertainty, my calibration and measurement capability? This chart says, hey, I need to find a better reference standard, a better reference lab. That's all it's telling me. If this is dominant, you could have a situation where something else is dominant and the reference lab's not going to do that much, and maybe you just have a bad instrument and you need to replace that instrument. So you keep doing the same thing again. Next step is do the same thing again for the next point in the range. You start doing this, it gets pretty easy. Only 3 things that typically change with the E74 cal: repeatability of the best existing device, reference standard uncertainty is probably going to change, and the stability will change. And then back in 2017, I wrote a paper using this concept, and here's all the uncertainty sources that we put in. We could have put in some more. We controlled this in our lab. Tier 0, that's dead weight. We were able to get 0.016. The next tier, when we calibrate that standard with dead weight, the best we could get at that 10 or at the 20% force point was about 0.02%. It says 0.1974, so we're just going to call that 0.2. And then if we took that load cell and we said, okay, now I'm going to use that load cell to calibrate something else, and I'm going to do all this stuff again, you can see some things got larger. We kept repeatability the same. There's some things specifically that would get a lot larger than what are here. What we purposely did in the paper is we said, okay, let's make assumptions that this is the best load cell and that our repeatability stays the same and our text reproducibility and reproducibility stayed the same. However, we have to carry that uncertainty for the reference. And when we do all that and ran the calculations, we got a number of 0.03 for the 20% point. Basically, what I'm saying is on tier 2, we said, hey, let's take the absolute best scenario that's possible, that could even be possible, likely never going to be probable, and let's see the best case we could possibly get. And we got to 0.031%. So what that says is if you're using dead weight, you can get much better than using the secondary standard, right? Calibrate dead weight 0.016, calibrate the load cell, you get 0.02 around there. Now you have to absorb that uncertainty, and assuming nothing else changes, which it absolutely will, the best I could get is 0.03. what this does is set a baseline to say, hey, if some labs out there are claiming numbers lower than this and they're at that tier 2, that is highly, highly questionable. So you can download our paper there, and then just looking at the different tiers and how it propagates. And then if we do the same thing for the next tier, it gets larger. We jump from 0.031 to 0.16. And expanded uncertainty is more than 5 times higher in tier 3 than in tier 1, assuming everything's good. Now, I said something about ISO 376 earlier, and here's just one slide comparing this. And if attainable, Morehouse ASTM method, we're basically at 0016. That's what we start at, particularly for our standards. And what's attainable with 1 or 3 reference force transducers, about 0.02%. ISO adds a lot more criteria like interpolation, percent zero reversibility, and they even add creep in there, and therefore that jumps to about 0.05%. So just something to look at, and just a slide to show what ISO 376 adds as far as things go that we're not getting with some of ASTM. We're not getting usually reversibility and creep and some other things. So that being said, almost 45 minutes as I was thinking, and using this proposed method, if you do everything well, you can possibly achieve about 0.02. The labs that I have helped over my time here usually get about 0.035%. And it typically comes up to they're using the right equipment, they're using everything else. It typically comes up to the operator's ability, and they get some high numbers, which I showed in the R&R between technicians. Though you can get 0.02%, especially if you use automation and some of the other the machines that like we have an automation machine that'll do better than any hold force better than any person. So you can achieve better with better equipment, though, like I said, or with more practice with the operators. 2 or more load cells. If you want to achieve that, you're not likely going to get it with 1 load cell for the range. You're going to need 2 or more, multiple load cells to get it, and they do need to be calibrated with deadweight primary standards. Other thing we have that I going through this slide, if you are interested, I said we had the 333-page book. We also have an email series. It's 35 weeks of emails, 3 a week, and all but 2 are just learning. And there's one to the left on uncertainty, and that one, though it's a little hard to see, it says measurement uncertainty in the measurement of force, and this one is force measuring instruments for measurement or verification of force. So this is not E74. This is an uncertainty budget for if you were doing like something maybe with a specified tolerance, which we didn't talk about, but that's in the emails. The way we designed them is they are 10 minutes a day, Tuesday through Thursday, so you Monday and Friday off. And as I said, it's 35 weeks, and you just go through, read them, refresh them, and then after that, after the 35 weeks of emails, there's a question and some things that basically say, hey, do you want a refresher, like 1 email per week and all that. But our hope is it breaks it down as digestible material that you can learn from and then make better measurements. As I said, the first one's introduction, the last one's like thank you and all that, and there's one on culture too. And because we talk a lot about uncertainty of measurement, and you talk about repeatability and reproducibility between technicians, and if people know they're being watched, they will generally perform better than if they're not. So it's what we haven't talked about is engagement, and engaging your people, engaging your team, having the right management, having the right core values, having people show up for work that want to do a good job. And when they're engaged, they're less likely to make mistakes, and less likely to make mistakes, then you get less measurement errors that tend to happen when people are unengaged or some other stuff. So really important there if you're running process controls and everything else. That they're also good checks to use between technicians. So that being said, other things, if you like this, follow us on LinkedIn. Particularly, that's where you get all these announcements of new stuff and everything else. Free downloads, that CMC sheet on our website. Just anything, that guidance document, anything we can do, help PJLA, help anyone else, and just make better measurements. Like for years, I would just get emails and I would type things out, and I got smarter, I think in like 2015, and I just started writing all this stuff down. So now we have the documents, and I don't have to answer the questions anymore that would take hours of time sometimes. That they're all available, and we keep updating them, do everything else. So with that, thank you all. Hopefully there's some questions and answers besides the, yeah, well, I'll tell you what, I'll make the slide deck available. As I was going through it, I did see a couple Ks were not italicized, which drove me freaking nuts, and I saw something else. So I'll do some edits and send them to Tracy if PGLA wants to make them available. But I really want to fix my Ks.
All right, thank you, Henry. And yeah, if you want to go ahead and make those edits, we will make the slides available. The recording will also be available too for listening. Unfortunately, we won't have the edited slides, but we usually do make those available. Henry, I do have a question for you real quick. With your training, sure. Do you do measurement uncertainty, like calculations, I saw traceability? Do you do that for other areas or can relate to other areas of calibration, or just force?
Force and torque. I get asked questions. I divert that to experts because it's, I love the question. A lot of this can be applied globally, right, to many disciplines. Though if you don't know all these intricacies in tests, the answer, Trace, is no. I do it for force and torque. Okay. SPC process controls will help detect a lot of the different stuff, but yeah, there's so many nuances and variables in some of these that let the experts do it. And there's things that are super easy to miss, especially with the electrical. I know I do our own electrical budgets, and I've had people help me, and I've missed things along the way. So I certainly would not want to miss something for anybody else.
Okay. Did you have a question that came in? What is the recommended overlapping while using two reference load cells during calibration of secondary load cell?
Okay, yeah, great question. So I don't have a good recommendation. It becomes if you propagate your the recommendation is if you do your analysis with the uncertainties and you know what you want to achieve, then you go from there. Sometimes you'll need 5 load cells, and that might mean depending on what your range is, sometimes you only need 2. Euromet CG4, they kind of get into, if you want to maintain really low numbers, that you might need 3 to 5 transducers. For instance, what I was showing here, if you buy really good equipment, have it calibrated in dead weight, you typically will need 2 to maintain O2 or better. Most of the people I helped were around 0.3, like I said, we're around 0.35 and they were using 2. But the real answer is it just depends on how good. If you want to drive it down to 0.1, you're probably looking at 5. If you're okay with 0.2, you at least need that 2 to 3. If you're looking at 0.5, you probably only need 1 to 2, and depending on what range you want to go. But you really have to do the work and propagate those uncertainty budgets to know where things are.
Okay, we've got another question that came in. In an LIC, how are the results from the labs compared to one another? Is one lab a reference lab and the other is a test lab?
Yep. Yeah. If you do an ILC, which ISO 17025 allows, and Tracy knows this, right, Tracy? Yeah. If you could do an ILC, yeah, you could set them up a lot of different ways. So the standard basically says make sure you have a proficiency test plan, and in general, as part of that plan, hit the parameter at least every 4 years. I'm going to go a little bit beyond your question here. I like to buy a really good load cell, a really good artifact or torsion cell or whatever you're buying, no matter what parameter you're in. I like to buy a really good artifact, and I like to send it to a primary lab. And then after I do that, I can do my own ILC. Typically, what I recommend people do is do your own ILC, right? It could be bad. It could be you could find bad technicians. You could find whatever. And I say bad technicians. The people aren't really bad. It's just they're not doing something right, or they need some training, or whatnot. You're probably gonna find all sorts of errors, and then you can start working backwards on how do I correct these errors. I have this known artifact that I can use. And then after you start correcting all the errors with that and figuring out how to make the better measurements, reading the documents and doing the other stuff, now you can also use this artifact to do your statistical process controls because you bought something really, really good. This is like the gold of any lab, right? To be able to say, here is my artifact. I make a measurement once a month, whatever it may be. I'm just throwing arbitrary numbers out there. I make a measurement once a month, and all of a sudden something went bad in month 6. Well, guess what? Month 5, everything looked really, really good. So now all I have to do is look at this window is where did something bad happen between month 5 and month 6? And I'm not looking 6 months back or 7 months back. Specifically answer that question. Yeah, you can, one lab is the reference, one lab is the test. That's typically how the ILC, instead of like a PT with a star pattern and all these other things, I don't even know all the names of them anymore, I forgot it. Instead of that, you get the one lab, say this is the reference lab. I have this artifact. We have Excel sheets that you can use for it. If you want to do a true blind test, there are companies out there like Sapphire, NAPT, and everybody else that can run the data. And I certainly recommend doing blind testing after you've established that your measurements are as good as you think they would be, and get them in, and then document that. So when PJLA or any of the other ABs might come in, you can say, yeah, I participated. This is what we do. The technicians don't have the data, and we run this through, and this is what we get. And if you have the artifact, what's cool about it too, we had one company, they ran like 6 or 7 of their technicians. They just filled them all out in that Excel sheet. So you can probably, you can do whatever you want there. But yeah, that is answer the question. One lab is the reference, and then the other lab would be the test lab.
Okay, great. Well, I think that is all the questions we have today. If you can kind of go down the next slide there, I just wanted to project.
Yep, absolutely.
A couple things we have coming up. Some of you might already be aware of this, but just some upcoming webinars. In October, a webinar like this, we're going to be doing one on reporting of the results with Michael Tomasi and Michael Kramer. And then we have a series, educational series on our website. So we have some upcoming workshops. So the first one will be actually next week. So if you haven't registered, it's completely free. And it's an intro to internal auditing related to 17025. It's a 2-hour workshop through our Go to Training site. And then we have another free workshop on approaches to competence for personnel. So again, these are completely free. You get a certificate for the workshops, to show PJLA as your accreditor, or if you're not accredited by us, your accreditation body, that you're keeping up with the requirements. So please take the opportunity to take advantage of these free sessions. And there I included a link with our list of training. We have more throughout the rest of the year and more webinars to be announced as well.
Those are awesome, Tracy. Those are absolutely awesome.
They've been going great. I mean, we've had probably on average, probably at least 100 or so people taking advantage of the workshops, getting the certificates, and they, do a little bit more deeper dive than just, what a webinar can do. So I'm really happy to see the attendance rate on that. Lastly, here's our contact information. Henry's is below. Please utilize this website too. I love that you have a lot of training resources on there, and please take advantage of that. And if you have any questions, you can email Henry directly or myself, or anything that comes up with the webinar. If it does get to me, or through the end of this webcast, when you log out, we'll go ahead and get that to to Henry. So with that, I'd like to thank everyone. I think we have wrapped it up for the day. Thank you for attending. And Henry, thank you so much for joining us again. We look forward to having you back. You always have something new.
Tracy,
So,
thank you. There was one more question that came in. Is the
oh,
webinar
okay.
geared toward HR or is it generalized? And I think that was for the approaches to competence for personnel.
Oh, okay. This is geared, everything we typically do, if you go to the website, it's geared towards 17025. So that is 17025 section 6 requirement.
Yeah.
It's
But
gonna
I
talk.
can answer because I can answer in difference. If, you know, any good calibration tech is going to, one of the screening things that we figured out a bit later and avoided some headache was attention to detail. And that is one of the things that competency of personnel, of course, the PJLA have covered, but when you're hiring and on the HR side, it's that you really want people with or typically that are organized and that have a really good attention to detail.
Right, and you can, you could use some of the examples and some of the training approaches we're gonna go over related to really anyone in your company, but this is just, but again, this is kind of focused on the 17025, requirements. So yeah, I agree.
Awesome
Okay,
stuff.
all right. Well, thank you so much. We'll go ahead and wrap it up for the day, and we look forward to seeing all of you next week, if you want to join the workshop, or next month on our additional webinar. Have a great day. Thank you.
Thank you all.